Hello, good afternoon everyone. Good afternoon, Julien. Now we are going to talk a bit about electronics and the constraint of electronics in space, and in this new technology coming in space using the COTS component, but we will define all those terms. So, as explained in the previous presentation, space mission comes with some environmental constraints, vibration and shock induced by the launch, thermal dissipation and outgassing induced by the vacuum, and of course everything which is related to the radiation, since we are not protected by the magnetic field of the Earth. The single event effect that have some upset, functional interrupts and latch up that are caused to the triple E's. And as mentioned, triple E's means electrical, electronics and electromechanical parts. And of course today, this afternoon, we are going to focus on electronics parts. There is also the total dose accumulated during the mission, which is called TID, and this also causes degradation to the components over time. So in order to deal with this harsh radiation environment, some triple E's are designed especially to cope with them. So they are called radiation hardened or radiation tolerant components. So they are designed and manufactured with a highly resistant and radiation-induced failures. Some are totally hardened, other ones are tolerant, and during time the tolerances could diminish, but it's components that are relevant for a space mission. They provide high reliability in harsh radiation environment, but they come with some restrictions. So the cost is very high. With respect to the triple E market, it is a niche market, the component designed for space. So we have low volume, and it is requesting a huge set of qualification tests before being used on the mission. They have times to times lower performances due to the hardened technology that are used for those components, and again, because the niche market, the development and evolution cycles are quite slow. They come also with a bigger size in terms of packaging. Deltatec, that used to design and procure industrial electronics equipment, also design and procure electronics for space application using this rad-hard and rad-tolerant triple E's. So we have here on the screen a typical set of electronics designed by Deltatec. We focus on mainly two aspects, the cameras, the readout electronics for cameras. We have here the one for the Proba 2 mission in 1211 for the SWAP instrument, and more recently we launched 3 readout electronics for the Solar Orbiter mission on the EUI instrument. We also designed at Deltatec some data processing units that could be in order to store data, but also to compute things inside the mission. So we propose here some mass memory, some onboard computer, some payload data handling unit. This is things that are commonly designed and procured by Deltatec. So now the space comes with a change in terms of context. So more and more we can see that a reduction in the launch cost, meaning that with this new context, new needs are coming as well. So the platform and payload cost also must be reduced. We come from a single satellite mission with low revisit time, for instance, in Earth observation, to some constellation with a good revisit time, but also with a lot of satellites doing the same job, doing the same mission, meaning that a temporary unavailability is less critical with respect to a single satellite mission. The platforms are becoming smaller and smaller. If we compare the Dove platform with respect to the Sentinel platform for Earth observation, means also that the subsystem have to become what we call SWAP, small weight and power system. Since the bandwidth is still a limitation in the data transfer, we want to be more and more able to process the data inside the payload and to transform it in information. It was the main theme of the last 4S symposium last year, so doing information based on the data on board. And there is a newcomer also in the space industry, is that we want to have some platforms that are AI capable. So more and more COTS triple-E's are used in space. So COTS means for readily available, commercially produced electronic parts. So it comes from the industrial, automotive or military market. And the adoption of the COTS component is in good shape. So because the cost effectiveness, we have latest technological advancement and we have rapid development cycles. And we can see that those COTS components, for some of them, they have good behavior in radiation environment. And today we can see more and more companies proposing some test or a bibliothèque of COTS components suitable for the space application. At Deltatec, we already use COTS component for space application in 2010 for an onboard computer that has to be developed in less than 1 year and with a power consumption of less than 2 watts. We design an onboard computer using COTS component, but using a couple of mitigation like component redundancy, triple voting in some electronic system and so on. Recently, is asked Deltatec to design and manufacture a camera with high performances in order to make it flyable. So the data that has to be ingested and treated by this camera are quite high, and it was not possible to do it with a rad-hard or rad-tolerant component already available on the market. So in order to do that, we do what we called an hybrid architecture, mixing COTS component and rad-tolerant or rad-hard component. So we implement also what we called fault-tolerant mechanism. So we scrub the memories in order to check that there is no bit flip due to a single event upset or so on. We add some protection in order to prevent the single event latch up. We keep the high-end processing thanks the fact using COTS system on chip that we know are suitable for space application. In parallel, we keep the high-rel manufacturing and the high-rel and or military material and processes for such a design. So in order to be able to improve again this hybrid architecture, we will explain you, Julien will explain you how we add additional features in order to make it again more reliable.
Thank you, Eric. So Eric just mentioned the term hybrid. Hybrid architecture to improve systems reliability. But what does that mean exactly? What is hidden behind this hybrid term? To us, for Deltatec, hybrid architecture concept definition is to make the best of the two worlds, classical and NewSpace, to build a high performance equipment while maintaining the risk at an acceptable level. In this sentence, an acceptable level of risk is not a very accurate definition. It actually enhances the fact that this is mission dependent. As an easy example, losing one satellite in a constellation mission might be acceptable, while of course it's not for one satellite mission. Let's get a bit deeper in this hybrid architecture concept. On this graph, I'm plotting active components in a two-axis system. On the x-axis, you have the performance of the component, and on the y-axis, you have its cost. And there's actually a third variable, which is represented by the diameter of the dot. Here, I'm representing active components that are made for the space industry. These are qualified components for space environment. what do we see? We see two things. First of all, the bigger the performance, the higher the cost. This is very normal. Secondly, what we see is that the diameter of the dots are quite stable and quite good. It means that those components are made for the space environment and they have very good reliability. Eric mentioned that we are moving to a world in which COTS are widely used. Let's add them on this graph. We see them in blue. What do we see? Again, the better the performance, the higher the cost. Secondly, we see that for a given performance, a COTS component will be less expensive than a qualified component. This is also very normal. We see that COTS solutions propose components with bigger performances. And finally, about reliability, which is represented by the diameter of the dot, we see that it's more variable. We see more variation in the diameter of the dots for the blue components. And we see also that the diameters of the blue components is smaller. Now, all of that to try to illustrate you the hybrid concept. The hybrid architecture concept is actually to pick up components of both sides. We will pick up in purple not so expensive, low performance rad-hard component. This is what we will call the supervisor. The supervisor will have a high reliability and therefore a high availability. And next to this supervisor, we will pick up components in the blue graph. We will pick up therefore COTS solutions that will propose high performances for a reasonable cost. This is what I will call the high performance computing unit in the rest of this presentation. What if now we illustrate this concept on a block schematics? I'm using same colors. So on the left you have the supervisor in purple, and on the right you have the high performance computing unit in blue. Each side of these solutions has its own purpose. In blue, the high performance computing unit implements the required functionality of the equipment. As an easy example, if the equipment is a mass memory, this is where we will find memory components and all the management components of those memory. Typically, this is where we will find high-performance components such as latest FPGAs, system-on-chips, processors, or DSP. And on the left side, in purple, you have this supervisor. Actually, the supervisor is in charge of what we call FDIR, so fault detection, isolation, and recovery of the equipment. Made with rad-hard or rad-tolerant components, with its high availability, the supervisor will make sure the equipment remains in good health, even in case of a failure occurs in the blue side of the equipment. The supervisor will anyway remain available to provide to the platform the health status of the equipment, and it will take in charge the recovery in case of a failure. Let's get now a bit deeper into the details of what the supervisor does. So it does fault detection, isolation, and recovery. This is a non-exhaustive list, and this is providing you 4 examples. First of all, about power supplies. The supervisor will detect overcurrents, over and under voltages. As an example, a radiation effect could generate a latch-up in an electronic component. A latch-up is a phenomenon that occurs when a parasitic structure within the IC becomes conducting, creating a low-pass resistance between 2 power supply rails. And this leads to a sustained current that flows and can cause a component to malfunction or even become permanently damaged. To mitigate that high risk, the supervisor continuously monitors the supplied current, and in case of an overcurrent, it can shut down the concerned supply rail. Secondly, about memories. There are a lot of memories inside an electronic equipment. And it must be known that the radiation effect can generate single event effects such as single event upset. By upset, I'm meaning a bit flip, for example, in a memory cell of any memory. To mitigate that risk, we implement memory scrubber mechanism. What is it? This is actually a mechanism that will be managed by the supervisor and that will continuously read the memories, try to detect errors, and in case it can, it will correct those errors. In case it's not possible because there are too many cells to correct, the supervisor can decide to reset the system or even to restart the system. As a third example, we can implement a watchdog between the high-performance computing unit and the supervisor. This mechanism is actually a mechanism that will detect any misbehaving processing element of the high-performance computing unit, and in case it finds some misbehaving element, it will decide to reset or to restart the system. And finally, one last easy example is environment checkup. The supervisor can continuously monitor the environment of the equipment. As an example, the temperature is an easy example of it. In case it detects a temperature that goes too high, it can decide to shut down the high-performance computing unit, waiting it for cooling down. So, depending on the design, the risk to have a permanent failure in the COTS or the NewSpace part of the design, so on the blue part of the design, may exist. As a recover mechanism, redundancy can be implemented at equipment level. On this figure, we see that we have one supervisor in purple, but we have two high-performance computing units, one nominal and one redundant. In case the supervisor detects a permanent failure in the nominal high-performance computing unit, it can decide to turn it off forever and to use only the redundant unit for the future. And it must be pointed out that the limited cost of the NewSpace part of the design is less an obstacle for redundancy implementation. So Eric mentioned it in the beginning of this presentation. Artificial intelligence is becoming more and more important in space applications. For example, in Earth observation, cameras are generating more and more data, and it becomes very complicated to download all those data on ground. Automatic event detection algorithm, mainly made with deep neural networks, can be an answer to these downlink limitations. But powerful coprocessing components that permit to execute efficiently those deep neural networks inference are not components that are developed for a space environment. These are COTS. And these are not rad-hard or rad-tolerant components. And therefore, our hybrid architecture is particularly well adapted to integrate those type of components. And this is what we say, why we say that the hybrid architecture is an AR enabler solution. Well, up to now we have discussed about hybrid architecture for main electronic components, mainly active components. But the purpose of this slide is to mention that this hybrid concept not only applies to active components, but also to other elements of electronic equipments. First of all, there are passive components. Space-qualified components can be selected for the supervisor, so I'm talking about resistors, capacitors, inductors, while we can select automotive quality level components for the computing unit. The same approach can be followed for the PCB, manufacturing or assembly. So there are space-qualified flows that are defined in the ECSS standards from ESA, and that can be followed for the supervisor side of the designer. While we can use more industrial standards, such as IPC, which stands for Institute of Printed Circuits. These are typically the standards that are followed for the automotive equipments.
Even military.
Even military, yeah. And last bullet, it's about development. The hybrid concept can be followed also at a development level. The question about the quality level for software or firmware development is a very interesting question. But that would take time to discuss in details, and maybe that's an interesting topic for next webinar. So, last slide for me. I'm trying to now illustrate what I've presented before with an example we are doing at Deltatec for the moment. So we are currently developing the LOIS payload computer. So LOIS is an instrument with two cameras, one hyperspectral in the visible range and one hyperspectral in the shortwave infrared range. These flight models will be delivered in 2024. And the hybrid approach hybrid approach has been followed for the payload computer of this LOS instrument. The main functionalities of these payload computers are the data ingestion of the two hyperspectral cameras, so the near and the sphere. There's also the mass memory of the instrument inside it. This is done with an SSD of 1 terabyte with a high bandwidth of 500 megabytes per second. We implement hyperspectral image compression, data encryption, and CCSDS packetization. You see a figure on this slide. I'm using the same colors as before. So we have in blue the high-performance computing unit, and in purple we have the supervisor. So all the functionalities are implemented in the blue side of this design. This is done with a system on chip from AMD or Xilinx before, and this is a Zinc component. And we have a supervisor made with a rad-hard controller that implements the full detection, isolation, and recovery of the whole systems, keeping a permanent link for health monitoring with the platform.
Thank you, Julien. That was clear how we implemented these hybrid architectures, and it allows us to keep up-to-date technology with higher performances available on the payloads. The AE enabler are more and more things that has to be implemented. It also allows to reduce the development and procurement time due to the availability of the COTS component with respect to the high-end rad-hard and rad-tolerant component. Of course, because we want to use this kind of system in constellation, reduced cost is an asset, and it allows this. The management risk then to supervision is quite important. So at Deltatec, we decide to not do system with only COTS component without having this supervision. And as mentioned, so the constraints of the constellation are coming, time to market, reduced cost, and these hybrid architectures allow to embrace these new constraints.
Thank you, Eric.
Thank you, everyone.
I think we have several questions.
There are several questions popping on the screen.
Yeah.
So the first one, I will take it. The data compression standard in the space industry is looking at, it typically depends the kind of data to be treated. So here we put an example of two hyperspectral systems, and those two hyperspectral systems are using CCSDS 123 compression. But one can imagine that JPEG compression and so on could be also implemented.
Yes, and for panchromatic images, we can follow CCSDS 122.
Yeah, as well.
This is also on this one that we have some experience. But yeah, as Eric said, we could use any let's say, industrial standards for compression also. With the COTS in space, it allows us to use very complex also algorithm for data compression. It can be lossless or not. Yeah.
So the second question, I guess we are going to iterate on it both. There is a trend to use AI for fault detection, isolation, and recovery monitoring of system. Is that run on rad-hard system or rather on COTS, and why? So what Julien demonstrated on our architecture is that we use rad-hard system with lower computing performances. So today, if we have to implement some AI, we would do it on the COTS part of the design.
Yeah, and yeah, about AI, we are used to work with deep neural networks algorithm. To do that, we need a nice, let's say, training set of data to train those algorithms. It may be complex to do that. So we are not used to implement AI algorithm for fault detection, isolation, and recovery. So maybe we cannot go, let's say, into details about that question. Yeah. Sorry.
Do we have practical experiences that we can share with cold and hot standby redundancy? So what we have demonstrated here is that for the the payload computer shown during the hybrid architecture presentation, we have a cold redundancy there, meaning that we duplicate as well the supervisor part of the system. But one could imagine that having one supervisor for two high-end processing system could be enough.
So indeed, for the LOIS example I showed during the presentation, we implement cold redundancy, but I didn't show it on the screen. The figure was like duplicated, one nominal and one redundant, but there was two supervisors in it. So cybersecurity is taking off everywhere. I assume X509 and PKI systems are entering into that satellite market as well. Can you share some thoughts? So indeed, cybersecurity is a growing question in the space market. However, at Deltatec side, we are more involved in the instrument side of the mission than on the platform sides. And the cybersecurity issues mainly comes from the communication links between platform and ground. So we are not deeply involved into those questions, unfortunately. And yeah, this is a very moving area, so we are following it. But I'm not sure we are well placed today to provide you, let's say, a detailed overview of cybersecurity for space applications.
But this is something typically we are starting to address at flight segment level.
Yeah.
The next question is how do you characterize the COTS component, for instance, the SSD in the diagram, to know the possible single event effect events in. So it is the approach is to choose COTS component that either have return of experience from space mission or that are provided with some radiation testing results. So typically we are not leading a test campaign on COTS component at our level, but this is something that we would be able to do. So we are in discussion with some partner in Belgium. So there is the CRC in Belgium where some tests could be done. We do it typically in TID when TID level are not available, and for SCE, if needed, it could be done also. But so far, we are using COTS components, COTS system that comes with their own information about the single event effect capabilities.
Yeah, that's the same question with the Xilinx system on chip we used. We didn't perform our own characterization of the sync component into radiation, but there are a lot of data on that topic, and we use it to characterize its behavior and also to, let's say, predict the statistics of the probability or the probability of a single event effect in that type of components.
Okay. Since there is no more question, but if you should have any question, do not hesitate to contact Deltatec. So visit our website www.deltatec.be in order to contact us.
Yes, thank you very much.
Thank you everyone, and have a good end of day.